Hello, this is Junichiro Horikawa. Today I'm going to show you how to create a autostereogram in Houdini, which is a single image stereogram designed to create visual illusion of a three-dimensional scene from a two-dimensional images such as these images. And in order to see the 3D image out of these 2D images, you have to change your focus distance of your eye using either cross-eye versions or walled-eye convergence. Most of the time you use this walled-eye convergence type to see the 3D image out of these 2D image by say that these dot line are the image plane, and the focus distance, the focus point of your eye should go farther than the image plane. So something like you're focusing way back of the image plane that you're looking at. If you use a cross divergence, then the focus point of your eye will be much closer than the image that you're looking at. So somewhere between your eyes and the image plane. But most of the time, the examples are using this walled eye. So today's implementation is also based on this walled eye convergence view type. So for example, for this kind of image, if you use a walled eye convergence, you can somehow see a silhouette of shark in 3D. So try that yourself, and if you can see that, then the things that I'm going to tell you right now should be really interesting, right? And in order to implement that, there is a paper explaining how to implement this with some C code. So I am just going to use those code written in C inside Houdini, translated into Vex code to actually implement this. Right, so let's start doing it. So just let me just tell you the basic algorithm how this autostereogram implementation works. And first of all, say this is the image plane. This square is the image plane that you're looking at, and these are your left and right eyes. And on the back you will see there is a 3D object that you want to view it as an illusion from on top of this image plane as an image, random dot image. So in order to do that, first you cast a ray from both eyes to one point of an object, something like this. And by casting a ray to the specific point on our object, you should have two intersected points on an image plane, and that intersected point should have the same color. So that's the basic rule here. And if you're looking at the different point on 3D objects such as this point, and if the casting ray casted line have an intersection which goes to here and here, and if the intersected points is sharing with the other ray casting points, ray casting lines, then that means this point also has the same color. So that's the basic algorithm. By setting the color the same for all the sharing intersected points, you should be able to have a illusional image on top of this image plane. And this is the detail algorithm showing how to implement this. So this is the eye, say this is the left eye and this is the right eye, and being separated by a distance e. In this case, the distance is kind of fixed, but you can also change that. And this is the image plane position. So have the distance from the eye, named D, and the farthest point of the focused point will be using the same distance D from an image plane. So something like this. So that's the basic setup. And if you are looking at the farthest point, which is on this plane, then the distance between the intersected points, which in this case, this point and this point, from left eye and right eye, then this distance is the farthest intersected distance between two eyes. So the distance between the two intersected points never go bigger than this far value. So this S, which is focusing on some point where the 3D geometry exists, is always less than this far. So that's the basic rule. Right? And when the place where the 3D geometry is placed is defined by a value z, which is from 0 to 1. 0 means it's on the farthest point, farthest distance, and 1 means somewhere in between the image plane and the farthest plane. And this distance of this depth of this 3D image, 3D object, is defined as mu d. And d is equal to this value, and mu can be any value, but in this case it's using a constant value, 1/3. D and mu is using a constant value 1/3. But you can also parameterize this to control the depths. Like if you use 1 second, then the depths will be something around this. But if you make the depths big, like this big, then the 3D image will be strongly distorted, so it might be hard to see the real image. So as a best practice, it should be better to stay as a 1/3. Right? And so that should be the basic concept, basic diagram showing the algorithm of the autostereogram. Another value that you might need to see is this value, which is the distance between the eye to the focus point. And this value, 1 minus mu z multiplied by d, is the distance from the plane to the focus point. So remember all that variables, and by using those values, we are going to implement this autostereogram using this code. Right. Let's do this. So I think I am going to place this on the left side so that I can see it while we're doing the coding. And let's open up the Houdini empty scene and start writing the code. Right. So first of all, let's start by creating a geometry node. And let's think about what kind of parameters we could have. One parameter we could have is the size of the image, so on the width, for the width and the height, right? And also we could also control the value mu, which was 1/3 in this paper. But in order to test out the other parameter other values like 1 second or so, we could also parameterize that as well. And another parameter we could set is the distance between two eyes. In this case, this is set as 2.5 inch, but we could control that by ourselves as well. Alright, so let's do this. So in order to set the parameter, we are going to start by creating a null node, creating a controller, no controller, set in some color, and let's have full values. One is a width of the image, so I'm going to use an integer, and I'm going to name as xnum. And also let's set the height. I'm going to name as ynum. Right, and I'm going to set the range of these two values from 0 to say 512. 512. Right, let's check. Right, then let's also set the mu value. I'm going to use the float. And since the value will be something 1 divided by something, so in case of 1/3, it is 1 divided by 3. So I'm going to just use a value from 1 to 10, and if the value is 3 for this mu, then the actual mu value will be 1/3. Right. So let's set the mu to 3, xnum to say 256 as initial value, and y as a 128 as initial value, which is going to be the height. And let's also set the eye separation value, eye separation distance, and let's set the range from 0 to 1. We're not sure yet what's the best value for this, so I'm going to set as 0.4 for now. Alright, so first of all, we're going to create the basic grid geometry in order to make it as a base image plane, where we're going to set the color for each square, each faces. So I'm going to use a grid first, place the grid, and in order to use it as a color plane so that I can change each face as like acting as a pixel, I have to change the number of rows and columns based on the resolutions. And that resolutions comes from the parameter that I have set, which is xnum and ynum. So let's copy xnum first, then go back to the grid, and then paste that to a column first. And I'm going to add 1 so that the number of columns on the horizontal direction will be equal to 256 in this case. Alright, and the ynum, we can also copy that value and then paste this to the row of grid +1. Right. So currently the y direction also has the number of faces as the number of 128. Although right now the aspect ratio of this image is a bit wrong, so I have to fix that by changing probably this size value here. I'm going to make it simple, so I'm going to make the size of the width as 1, and I'm going to change the size of the height value by using ynum and xnum as a aspect ratio. So to do that, what I'm going to do is to first copy this ynum value, then divide by this xnum, and as a result, all the square face should have a square looking geometry, and the total size will follow the aspect ratio between the width by height. So in this case, the width is 2 times bigger than the height, and this looks correct, I think. And the value, the width is always equal to 1, so which is convenient when you want to set a value like eye separation. Okay, and I think I made a spell mistake here. Let's go back. Sep, right. Okay, so far so good. Now let's create some basic geometry which you want to show as a 3D illusion. Alright, so to make it simple, I'm going to first create a text geometry, so that by changing your eye focus to world eye conversions, then you should be able to see the popped up text out of this 2D image. Okay, so let's create a font node, and the word could be anything. I'm just gonna say hello. Maybe I could parameterize this as well. Maybe go back to the null controller, give a string parameter, maybe on top, text. Okay, and say hello here. Copy this parameter, then go back to the font, paste this parameter using paste relative reference, and then right now the geometry, the font is on XY plane, so I want to place it on XZ plane as this grid is right now on. So let's rotate this font minus 90 degrees on X axis like this, and I think the letter hello is still too big, so let's scale this down a little bit. Okay, maybe 0.2 might go well. Yeah, I think that looks good. Alright, now next thing I would like to do is to set the height of this text, but I can do that later using a point wrangle. Let's use the point wrangle to actually raise up the vertex which is inside this hello letter. So for example, if these vertices are inside this hello plane, hello word or hello letter, then raise up these vertex upward, with some specified distance. If the vertex is not inside the hello letter, then keep that distance as 0. So that's what I'm going to do in order to create the extrusion using this hello word. I'm going to use the point wrangle like these, connected like this. Let's name this Geom. Open up the code. Right. And in order to lace up the word, first I need to check if the points on the grid is inside the letter hello or not. So to do that, I'm just going to check the shortest distance between the point and the letter. So if the distance is really close to 0, then that means it's inside the letter. Okay, so the shortest distance can be retrieved using a function called xyz_dist from the second input using the point position value. Okay, and let's make the condition if the distance is really small, equal to 0. So say less than 0.01, which means it's really close to 0. Then let's set the y value of the y coordinate of the point to 1. So raise up the point upward. Let's check. Alright, it's working. Now it looks like it's too much extruded, but it doesn't really matter. For now, the actual extrusion distance is not like this, but it is going to be multiplied by a 1/3 of a parameter, which is this one. So currently what we have achieved is this value from 0 to 1, this z value. So we have just set the text height from the farthest point. So currently think that this is the grid position, current grid position, and we have just created the text which goes from 0 to 1 using this z as a y value. This one. So the height of the text is at the maximum in this range, which is 1/3 of a d. Right. And just having a text might not be really interesting, so I am going to add another animated geometry to make it a bit more interesting. So I'm going to create a kind of a wavy pattern in between the flat plane and the hello extruded geometry. So something having a wave, something like these, and also be animated using a frame count or time frame. So to do that, I'm going to use the else condition, and if the point is not on the font, then change the height to something using a noise function, using a p as a point position as random seed, and probably using a frame as a seed as well in order to create an animation. And this might be too much, too big. Maybe I could also use sine wave so that I could create a repeated wavy pattern using a time frame. So say the whole time frame is 180 degrees, 180. Then I could multiply this frame by 2, then at 180 at frame 180, this at frame by multiplied by 2 will be 360 degrees, so that this sine will be repeated from 0 to -1 to 1. Now, in order to use this as a degrees, I think I also need to set the radians function to convert this into radians so that I can use it with the sine wave. Alright, so I think this is okay with the noise. Let's check how it looks like. Okay, so I do have a wave pattern like this, and if I play it, yeah, I do have an animated wave, and is repeated from 0 to 180. Okay, so far so good, but the height of this wave is a bit too low compared to the hello, so let's also change the range of this wavy height. Since I am using a noise function, the noise function is theoretically the minimum value is 0 and maximum value is 1, but it's often go from 0.25 to 0.75. So let's remap this value so that the range will go from 0 to 1 in bigger chance. So I'm going to use a fit, and from 0.25 to 0.75, I'm going to set to 0 to 1, and we don't want to go beyond 1 or below 0, which is going to be negative, so I'm also going to clamp this to 0 to 1, just in case it goes beyond or below 0, like this. Okay, now let's check this again by playing it. Okay, looks good. If it goes beyond 1, then at some point it is clumped to the distance, the height will be clumped to 1. Somewhere like around here. But it looks good. It looks just fine for my use case. So let's keep it as it is. Alright, now is the time to set some parameters. I'll set some attributes for initial attributes in order to actually implement the code written here in this paper. Okay, so in order to calculate, in order to use this algorithm, first of all, what we need to have is let's go back a little bit to this flat plane, and what we need to have first is the x-index of each faces. So say starting from 0, the x-index should go 0, 1, 2, 3, 4, 5, and so on. And if you go down and start from this one, this also should have an x-index 0 and goes to 1, 2, 3, 4, 5 if you go to the right side. And the y-index, for y-index, this top left corner should have a 0 as a y-index, and if you go down, then the value goes to 0, 1, 2, 4, 0, 1, 2, 3, 4, 5, 6, and so on. And that's the same for any place on top. If you pick this face, then the y-index of this one is also 0 and goes to 1, 2, 3 if you go down. So we want to create that kind of parameter attribute to each faces, and I also want to get the height value from this geometry which is converted, which the height of the value has been being created. So I'm also going to retrieve the height for each faces and set it as a primitive attribute to each grid face. So 3 attributes I want to create: the x-index, y-index, and the height or the depths of a plane to see it as a 3D illusion. Okay, so to do that, I'm going to use a primitive Wrangle. And let's name this init, initialize init. Okay, let's open up the code editor, and then let's set the x-index and y-index first. In order to do that, I need to have a maximum x number. So let's create a parameter called xnum. Promote this, and to this xnum, I'm just going to copy this xnum value, which in this case 256. Copy this, paste it right here. Oops. Paste it right here. Right. Okay. And let's go back here. Let's name the attribute x-index as an x, and this x value can be calculated like this. First, retrieve the primitive number, which goes from 0 to maximum face number, which you can see like this, and the maximum is 32767 or something. Right. And by calculating the modulus with a xnum, you can actually retrieve the x-index of each faces. For the y-index, what you just need to do is to divide this primitive number by a x number. And just in case, I'm going to use a floor function to make it as an integer. Right. So let's check the primitive attribute if I have those necessary attributes here, x and y. Okay. Now let's also check on top of the plane if the x-index and y-index seems to be correct. Okay, so I am going to check that by creating this marker. Click this plus marker. First of all, I'm going to check the x-index by setting the attribute to x. Okay. Let's also create y-index. Y. Let's set the color to something different to the x. Right. So the blue one is x index, and let's also give the text size a bit bigger. Go to the guide font, large, and also let's set the background to dark. Alright, so if you look at the blue text, it starts from 0, go to incrementing the value by 1 if you go to the right side, and stops at 256. So starting from 0 and end at 255 means that there are actually 256 faces on horizontal direction. And if you go at the far left, the x value always starts at 0, so it looks correct. If you look at the y, which is this red text, the top part always starts from 0, and bottom face always end at 127, so this also seems correct as well. So that should be okay. Now let's also transfer the height value from this geom to this grid faces. Go back to the code, and which is also easy to retrieve. First, I'm going to retrieve the point position from the second input by, let's name this gpos, and using the prim attribute from second input, get the position value, the center position of the grid face at same primitive number as the first input. Right, and let's set the z value, z attribute of each faces as a y coordinate from the second input. If you see it, then the value z will be created, and that value is in between 0 to 1. And the text is always at the position 1. So you kind of can see that at 1 there should be some text letter exist. Right. Enough for the preparation. It's actually time to implement this autostereogram code from this PDF. Okay, before going to the implementation, the name of this paper is called Displaying 3D Images, Algorithm for Single-Image Random-Dot Stereogram. And this paper was written by Harold W. Timbleby from University of Stirling, and Stuart Inglis and Ian H. Wetton from University of Waikato. Right. Okay, keep this on the left side. Let's give some space like this. Okay, so let's check out the code, how to actually implement this. And seems like it is defining some of the constant value, or the functions, like how to calculate the round value. I don't think we need to implement this one, like DPI. Okay, we could also we don't have to, since we're not using the printing image, but it is actually a virtual image, we don't have to follow this DPI setup. We can just use the eye separation value that we have set up right here instead of this DPI value, as well as this E value. So we're going to replace this with a eye separation value. And for the mu, we do have the parameters, so we could also replace this with these. And the separation z, this is the function. So for this one, we could implement this as it is. And far separation 0, far is this value here, and we could just get that by setting the parameter 0 to this separation function right here. So this z value means that, I think it's the depths. So by setting it to 0, then 0 means this is the z equals 0 position. So that means the focus point is right here. So as a result, you should get the far distance between two intersected points. So we could also get that. And this define max x and max y is the size of the image, and we already have that value here. So we could also replace that. And inside the code, first of all, it is using the for loop for each y value. The y value means is the rows, for each rows. Okay, so for that, and so basically it is calculating each strip, the horizontal strip. And that means we could skip that part by using a for each loop in Houdini for each by retrieving each strip by strip, each row strip, horizontal strip, using for each loop, and that without using this code, so that it should be more could be more faster. Maybe not. Okay, for that I'm going to use this for each number. Or maybe, since this is based on the y direction, we're just going to retrieve each row one by one, and each row has different y value, y attribute. So we could get the for each based on that attribute. So instead of using a number, I could just use for each named primitive. Okay, and I could change the piece attribute to y, and as a result I could retrieve the horizontal strip one by one, like this. Yeah, looking good. Okay, so this part, this for each loop part, is on this for loop for this y, which goes to somewhere around here, right? So we already have just implemented this code, this first line and second this end for loop code with this for each loop. Now let's get writing some code which is inside here. Right, and we cannot kind of use the another for each loop inside, because there are kind of a recursive function right here, which is using a do while function. So which is not really a recursive, but it's better to do it by code, and we somehow it is written in C, and the Vex code is actually based on C as well, so it's pretty easy to implement this using Vex actually. So let's do that. Alright, and what I'm going to use is attribute Wrangle, and I'm going to set the run over to detail so that I can calculate the point one by one using a loop method. So that's kind of a reason why I set the first while loop as a horizontal for each loop, because if I use the detail instead of this for each loop, then that's going to be really slow, since there are no ways to calculate parallel. But for the x direction, for the column direction, we cannot kind of use we cannot use the for each loop, since we have to, as I said, kind of do the recursive calculation for each faces from left to right. Alright, let's open up the code editor and start writing some code based on this code written in this PDF. And first of all, I'm going to bring up some of the parameter that I need to use. First, instead of this dpi and capital E, I'm going to bring up the I separation value. So I sep. Okay. And let's also bring up the max x and max y. But I don't actually need this max y because it is only used in right here, and we already have implemented using for each loop, so I just need max x. So instead of naming max x, I'm going to name as xnum, which is equal to the xnum in controller null node. Okay, let's name as xnum, and another variable or parameter I need is this mu value. So let's bring that up. So float mu is equal to 1 divided by mu, which is in between 1 to 10 in the controller. Right. Anything else? I think, okay, if I look at carefully, I think I made some mistake. Okay, so before I said that I don't need dpi and capital E, but actually what I don't need was just this dpi. The value right here inside the E 2.5 multiplied by dpi is the actual I separation value, how much the I is separated. So that means I still need this capital E. So let's create the E value as well. And it says the E is rounded value of I separation, so we can use rint and I use I separation. But actually this value itself, it's not just I separation, because I separation currently I have set in it as a value between 0 to 1. So if I make this as an integer, it always becomes 0 or 1. That's not the value that I want, but it actually, in this code, the E means the number of pixels. So to make this value as a number of pixels, I have to multiply it by xnum, so which is the maximum number on x direction. So if the xnum is 256 and if the isep is 0.5, then the actual resolution is 128, which is the distance from left eye to right eye. So I have to write like this, and the E is actually an integer. Okay, so that's the parameter, and other stuff that I need to implement is these functions like separation and var. For that, I could directly use this define and separation z using round. I might need to define the round as well for this one if I want to use it inside the define. Define round x int. Okay, cannot really see what's out there. Int x plus rate 0.5. Okay, And for the separation, it is round 1 minus mu multiplied by z multiplied by e divided by 2 minus mu multiplied by z. Okay. Define far is calculated using separation 0. Right. So this separation is actually the distance between the two intersected points on the image plane. Apply. Let's see if there's no errors. Looks good, I think. And I don't actually need a max x and max y because I already have it. So let's starting writing the code from here. Okay. Now let's make the size a little bit smaller. Okay. Now first of all, we need some parameters like these, like integer pix, integer same, integer s, and integer left and right. Integer pix is the array, which is the color of the pixels. And it is using integer because in this paper the image is drawn as black and white image, but actually for me, for this example, in this Houdini example, I want to show the color as a RGB color. So instead of setting the integer array, I'm going to set it as a vector array. So vector pix, create an empty array. And for the same is to check whether the left eye and the right eye have the same color. So that's the array to store the checking value. So for that I can just use integer. So name same and creating the empty array. Okay, for s, this is the stereo separation at xy point. Now could be just an s for now. And left and right, the x value corresponding to left and right eyes. Okay, so that's the x coordinate, x index of left eye and right eye. And for now we don't need to store any values, so I'm just gonna write left and right like this. Okay. Right, so let's start coding the first line. For x equal to 0, x is smaller than max x, increment x by 1, and same x is x. So each pixel is initially linked with itself. So what I'm gonna do here is to store same array using the x index value. So that should be easy. It's like a initialization for a same value, same array. The max x is equal to xnum. Okay, so same. I'm going to use the push. Push same is equal to I. Right. Yeah, instead of using x, I used I right here. Doesn't matter which one it should be. This could also be replaced with x. Okay, and I am also going to, it doesn't written right here, but I'm also going to initialize this pix array. since in this example the number of array is defined for both picks and same, but for myself I haven't implemented the number of arrays. Instead, I am going to set the number of arrays using this for each loop. So for picks, as a default value, I'm going to set 111, which is equal to white color. Okay. Now let's go to the next part, which is below, underneath this for loop, from here to somewhere right here, I think. All right. So for this one, it's using another loop looking at each x value, each x indexes. So let's give another for loop to be able to see a bit more, to be able to implement it a bit more easily. I'm going to set the integer value to x instead of I, as I did it here. Okay, x is smaller than xnum. It is essentially same loop as I did here, so I can just also replace this I with x as well. Might be better that way because it's easier to see. Right, first line, setting the value s, which is this one, as using a separation function zxy. Right. And this zxy is the depth of an image at xy position. And you can actually get this depth value from a primitive attribute, actually, which is a z value. If you go to the geometry spreadsheet, this z value is the actual depth value corresponding to this zxy. So it's pretty easy to get that value. So let's get this value first. Float z is equal to primitive 0. Name of the attribute is z at x index. So this is equal to this zxy. Right. Then using this z value, I can set this s value by using a separation function using z as a parameter. Okay, no errors. Okay, next I'm going to set the s left value. So left is equal to x minus. Okay, so this equation right here is done so that this value, say this is t, should be always more than 1. So it should be something like this. So this value t should not be value 0, because in that case the left and right value will be the same value, and that means there's no separation between left and right. So we have to make sure that this value is always more than 1. Alright, so instead of writing like this, it might be easier to understand by writing it like max s multiplied by 0.5 is should not be less than 1 by using max function and changing it to integer like this. And actually we don't need this s. Okay, that's for the left, and for the right we just have to add s to the left value that we have just created. Okay, and there's a condition here. If left is more than 0 and right is less than max x, meaning left value, left index value, left x index value should not be negative, or right x index value should not be more than x num, because in that case there's no pixels exist on that index. So that's easy to understand. Left and right is x num. Okay, and this we're going to have some of another value right here, another parameter right here, I think, which is visible int t and the float zt. Visible is the value using to check if the surface can be seen from an eye point view or not. This is explained in this diagram. So say this is the 3D image right here, and if you trying to look in at this point, from the left eye you can see it without any obstacles, but from the right eyes, if you try to cast a ray, it is somehow blocked at this point, so you cannot actually see this point. That means we have to skip this point, and visualize is used right here. If this point cannot be seen, then the visual should be 0. If the point that you're looking at, then it can be seen from both eyes, and in that case the visible is equal to 1. Yeah, this is visible. Okay, so that's the parameter that it's showing right here. And int integer t equal to 1 will check the points x minus t and x plus t. Okay, so in order to check how far we cannot see or we can see, we're going to, if we couldn't see the point right here, we're going to offset the point that we're going to looking at to check if the next neighbor point can be seen without an obstacle or not. If it can be seen, then we can define the value t. But if this next point is still blocked by an obstacle, then the t is incremented by 1, becomes 2, and so on, until you can find out the actual visible point. Alright, so that's what's it doing right here. in the do while function and do while loop until here. Okay, so let's have these three values. The zt is the coordinate of ray at these 2 points. Okay, so int visible, int t equal to 1, load zt equal to, well, it's equal to 0, I guess, as initial value. Alright, now let's write this code. We can, since this is written in C, we can just follow the syntax written like this. So let's do this. First of all, do, and when you use this do loop, try not to apply quickly, because at some point there's going to be an infinite loop if you are missing some of the code. So try to click apply when you have written all the code for this kind of loop, do while loop or while loop. Right, so for do loop, first of all, we're going to create a zt value. Right, and this zxy is equal to this value here. So z plus 2 multiplied by 2 minus, 2 minus mu multiplied by z multiplied by t divided by mu multiplied by e. Okay, and for the visible, in order to calculate the visible, we need to have this zx minus ty and zx plus ty. Now this is not equal to z, obviously, so we need to get that value using from the primitive attribute. So say this is the left side z value and this is the right side z value. I'm going to name the first one left side z value as lz, which you can retrieve by accessing the primitive attribute at x minus t. Same for the our z, primitive 0 z x plus t. Okay, now it's time to calculate the visible. Visible equal to lz less than zt and rz less than zt. And it said false if obscured. So if it's blocked by the obstacle, then this is going to be false, which is equal to 0. If it's not, then it's equal to 1. Right, and increment t by 1. Alright, now make a condition for the do loop using while visible is equal to 1 and zt is less than 1. Okay, now I think I have written all the do loop code. Let's click apply. Okay, seems no infinite loop here. It's great. Now let's make sure I don't lose anything, so I'm going to save this. Okay. Okay, let's bring this a bit to the left. Now I have implemented this code. Now it's time to check if the visible is equal to 1 or equal to 0. If visible is equal to 1, then the point is that you're looking at can be seen. So if visible, then first of all, create a variable called k, so integer k equal to 0, and for k equal to same left. So this is where we're going to check if the left and right side index is same, having the same color or not. K equal to same left, k is not equal to left, and k is not equal to right as well, and k is equal to sample left. Now obviously we have to update the left in order to this loop to work. If k is less than right, which is around here, then left is equal to k, else left is equal to right, and right is equal to k, leaving the loop same left is equal to right. So setting the left side index color same as the right index color. Okay, should be the same around here. So we have it just implemented from here to here. Now it's almost done. The last part right here should be written right outside the whole loop. For int x is xnum minus 1, x is larger than 0, x minus minus. So this means that we're going to look from the right side of the horizontal strip. If same x is equal to x, then pix x is in this case it's using the random value, but instead of using random we could also set some value based on a noise value or so to make it a bit more like a pattern, a bit more like a smooth pattern. So let's use the curly bracket to give the if condition, and I'm going to first retrieve the position of the h faces using prim function, and use this as a random seed for the noise function. Okay, so pix x is equal to noise and set at position dot x multiplied by, I don't know, 50, 0, position z multiplied by 10 or something. Maybe we could also parameterize z's value to check in order to change the pattern. So let's have this as a parameter. How to name this? X noise. and Y noise for this one. Okay, and oops, I think I have some errors here. Where is that? Okay, cannot cast from float to int. Line 39, right here. Okay, it says cannot cast. Let's check how I set the visible. Okay, it is integer. Float CT. What if I set it as 0? Okay, still have the same error. 39. Using initialized variable visible. Okay, so I'm gonna set it as 0. Okay, another error. 43. Undefined variable sample. Did I use sample? Okay, should be same. Sorry for that. Alright. Spell mistake. Okay, now, so this is the created color using RGB, changing RGB value. We might also control some color by setting the red value for this color, created color, to be 0, so that it will be more bluish color, or bluish or greenish color. But you could also change that to Y or Z, or ignore this if you want. Okay, else in this case the pixel is same as pixels, same right here. Means left and right side color will be the same color. So pix x is equal to pix same x. Okay. Finally, we're going to set this pixel value, the color value, to each faces. Okay, to do that, we're going to use a set prim attriv, setting a color value for each faces at x number with this pix x color value. Okay, now that should be okay. The color has been changed. Not really. Set primattive. I think this is fine. Oh, but what I am missing is those parameters, these parameters. So I have to copy some of the parameters right from here. So first of all, let's copy this xnum to xnum right here. And for x noise, I'm also going to set the mu value here. Right? So copy this mu value to this one. Alright, and let's also copy the eye separation value here to here. Okay, and the x noise could be any value, let's say 50 and 10 for now. Okay, so now I see some greenish or bluish color right here, but for one horizontal strip. Now if I exit this loop, I do see some pattern right here. And if I change this X noise, say X to 20, 30, the pattern will change corresponding to this noise value. Okay. Maybe we could also parameterize this so that in here, let's have two value here first. Say pattern X, and the second one to be pattern Y, and set the range for both from 0 to 100. Okay, so set the first one to 50, second one to 10, copy this, paste it right here. Also paste it right here as well and replace X with Y. Right. And it looks a bit dark, so let's set the material to white, diffuse to white, so it becomes a bit more clear. Now let's set the view to top viewport, and at this point it is already, the autostereogram has already been created. If you try to see it with a walleye conversions, you should be able to see a popped up word saying hello and some wavy mountain. Now let's also hide the wires. Now let me check first. Now I think I am seeing some pattern, but I'm not really sure if I'm seeing the right pattern or not. Let me zoom this up a little bit. I'm not sure if I'm seeing the right pattern, so in order to check it, what I can do is to create a guide circle point, so that say you have 2 points somewhere around here and here, and by looking behind this image, and in that case these 2 points created will become 3 points when you look farther to this image, and that is where the focus point is correct in order to see the 3D illusional image. So let's create that, and it is explained right here where to create that draw point, 2 guide points right here. So let's first create that. Okay, in order to create that point, I want to place that point on top of this grid image, somewhere around here. So I'm going to refer to this grid where to actually place the point. So first of all, I'm going to create another attribute, Wrangle. Attribute Wrangle. Connect the grid to the second input, and name this as an eye position, set it to detail. Okay, and first of all, I can get the separation of these two dot due to circles, which is equal to this far value. So I just need to calculate that far value by first retrieving the separation value, eye separation, which is equal to this one. Let's paste that to right here. Okay, and if you look at this diagram, this far value is actually a half size of this E value right here. So easy to do, easy to calculate. You just need to multiply this separation with 0.5. So sep multiply by 0.5. So that's the actual size between the actual distance between the left and right circle. And next I want to get the boundary size of the grid. I'm going to use the min size, get b box min from the second input, and I'm going to create two circles. So I'm going to use for loop starting from -1 to 1, incremented by 2, so that the value I will be -1 or +1. Okay, and let's create a point pt, and pt is equal to add point set I multiply by sep multiply by 0.5, 0 min size z minus 0.0. This is an offset value from the top part of the grid. Okay, so now I have 2 points and the position of the grid is somewhere around here. So seems like a nice position. Now we can just copy some circle at this point position using a copy to point node. Let's create a circle first at x, z plane. The size should be any value, could be any value. I'm gonna set it to 0.01. Use copy 2 points like this. Okay, and finally merge this circle with a created grid pattern. Okay, so if you use wall eye convergence and try to have these 2 points merge together, this one goes to the right, this one goes to the left, and as a result you should be able to see 3 points if you focus on the back side of this image. And that's the point where you should be able to see a 3D image of from this grid. If I play it, okay, I think there is something wrong with this one because I don't see any animation. Okay, yeah, I think something is wrong, and I don't really see the hello is also looking a bit wrong right here. Yep, something must be wrong. Okay, let's check one by one. First of all, the z value. Let's check if this z value is first of all correct. Let's go back to the perspective and try to replace the y value with this z. Cannot really see. Okay, I don't see any difference. Oh, that is because I'm using primitive Wrangle. Okay, forget about it. Although the value here is actually retrieved, so I think this one is okay. I think something is wrong right here. Okay, I'm gonna name this Single-Image Random-Dot Stereogram. Okay, now let's check the code. The point I should be careful is somewhere around here, first of all, I think. Okay. If I check the define, first thing I would like to try out is to say, so capital, the lowercase, uppercase is correct. Round. Okay, let's also remove the spaces. Separation. Yeah. 1 minus mu minus capital Z multiplied by E divided by 2 minus mu multiplied by Z. Okay. And for separation is separation 0. Let's check if this separation 0 is correct. If sep is equal to far. Okay, go to the geometry spreadsheet. And this was a primitive Wrangle, was it? Oh no, this was the detail Wrangle, so it says 51.0, right? And the total value of x is 256, and if I multiply this with 0.4, so 256 multiplied by 0.4, that's 120, and we're also going to multiply by 2 to get the far values, and that's equal to 51.2. So if the integer is equal to 51, that is correct. Yeah, that should be correct. So this define for the separation is correct. Okay, let's go further. This is initialization, doesn't really matter. And these should also be correct, I think. Let's check the number of same. If the loop has been correctly done. Okay, 256 seems okay. Let's also check the actual values. Actual initial values starting from 0 incremented by 1. That is also correct. Okay. Okay, we have the loop here. We are checking the primitive z value, calculating the separation, left and right. visible is equal to 0, zt goes to 1, zt goes to 0. Okay, and zt is z plus 2. Well, okay, I think this is this is something wrong. This must be something wrong. Okay, if I check this calculation, the t must go outside the bracket, but it's inside the bracket right now. Okay, so it should be written like this. Okay, this might have been the place where I needed to fix. Let's go back again. Looking from the top view. And if I try to see the image using a walleye, yeah, I think I'm seeing it. And if I play it, yes, I am seeing an animated mountain, wavy mountain, and I see a word hello. Yep, I think this is correct. This looks correct. Yeah. Yep. Okay, well, just having a word hello at standing like this might not be that interesting, so let me also try rotating this word using a y-axis just to make it a bit more interesting. So at rotate y-axis, I'm going to use a $FF multiplied by 2, so it will be rotated from 0 to 180 frame. Yep, I'm seeing it. I am seeing it. So both wave mountain and the word hello is animated. Okay, so that's pretty much it. Even if you change the resolutions from here, right now you have 256, but if you change the height to 256 as well, it still works. Should still be able to see the animated pattern. Yeah, it's a bit slow, but it's working. You can also change the pattern, like more horizontally oriented pattern, but you can still see the 3D image underneath, the illusional geometry underneath. Alright, and you can also change like the separation distance, eye separation distance. If you make it smaller, then you have more pattern and you don't need to have a strong convergence to see the image. So it'll be much easier to see. If you make it a bit more farther, then it's gonna be a bit harder to make the convergence. It's gonna take some time. If you're not experienced enough with this kind of magic eye view, it might be hard to really see it. So 0.4 something is a bit better. For mu, if you decrease this, you have more depths, meaning you have more distorted geometry, which makes you a bit harder to see the whole 3D geometry, but I think it's still working. Yeah. If you make the mu a bit bigger, then everything becomes a bit more flat, because there's gonna be less depths. So basically keeping a 3 is the best practice, but based on your purpose, you can change that value as well. Okay, so that's pretty much it. That's how you can create your own autostereogram using Houdini as a prototype platform. You can implement that to any kind of platform using this algorithm based on the paper that I showed here. Okay, so that's it. Thank you for watching, and let me know how you think about it. Thank you.